there has been some time spent here and there discussing the notion that position, velocity, and acceleration are vector quantities, and therefore they have two components that are linearly independent one from the other. By independence, I mean that the x-axis cannot be expressed in any way in terms of the y-axis, and vice versa. They are independent one from the other. The fancy word for that is orthogonal, things that are unrelated. Outside of the math context, sometimes I mention the colors, red, green, and blue. Well, that's not a mathematical idea unless you convert those into some number schemes we've done technologically. But red, green, and blue are linearly independent from each other, and every color can be made from a combination of the three colors with different weighting factors. That's an example of orthogonality and linear independence. So when I describe a position vector, R, which describes the position of a thing, and I write it in terms of its components, it has an x component which is directed along the x-axis, which I use this I hat notation to describe the x-axis and a quantity x along that axis, plus y in the j hat direction, and I could go to 3 dimensions by adding z in the k hat direction for 3-dimensional motion. The x and y of this vector are independent. By a combination of x and y components, I can specify any location in 2-dimensional space. That's the big idea. And the same thing is true of velocities, and this is really the issue of today, that a velocity vector has two components: an x component of the velocity, which is directed along the x-axis, and a y component of the velocity, which is directed along the j-axis. The x component and the y component are completely independent of each other, but together they can specify any 2-dimensional velocity vector, which points not just along the x-axis, not just along the y-axis, but any axis. And of course, it's similarly true that in 2-dimensional space, an acceleration vector has two components. It has an x component of acceleration that points along the x-axis, so that's ax I hat, plus ay, the y component of the acceleration along the y-axis. Now, what I'm going to discuss today is the evolution in time of position, velocity, and acceleration vectors in the context of motion under the influence of gravity. It is a familiar problem, the problem of projectile motion. We call it projectile motion because the instance perhaps that first comes to mind is firing a cannonball out of a cannon. I fill the thing up with some gunpowder and I put a cannonball in the end of the thing and boom, off it goes. When I launch the cannonball, it has both a horizontal and vertical component of its velocity. It has a total velocity vector at an angle. As such, its subsequent motion in time is vertical motion and horizontal motion simultaneously. Not to worry, these two motions are independent of each other. So really, when I'm solving a problem of projectile motion, I'm simply solving a 1-dimensional motion problem twice. Specifically in this case, my acceleration vector, which I've written here generally, in this specific case that I'm describing, this acceleration becomes acceleration along the vertical axis because the phenomenon of gravity is vertical. And so the acceleration vector in terms of what I'm describing today is negative g j hat. There is no x-axis component because for the moment, I am not considering that there is any influence that would change the velocity of an object horizontally. Yes, viscous drag, air resistance. But I'll eliminate viscous drag and consider only the motion of an object in 2 dimensions solely under the influence of gravity. So today, that's what I mean by projectile motion. So here's where it all begins, the source of it, is launching an object, cantaloupe, a chicken, your grandmother, with some velocity in 2 dimensions, which I'll imagine looks just like this. I just made that up, but there's a velocity vector, v, and I'll put a harpoon on because that's the way it should be drawn. And it's very sophisticated because it's neither horizontal nor vertical. It's both simultaneously. Well, the very first thing that I need to appreciate to make a start here is that this velocity vector can be described as components in a coordinate system that I choose. I choose. I mean, Shidley chooses. the initial position to be 0 and upward to be the positive direction. It turns out I'll also choose outward, that is to the right, and this diagram is positive as well. I choose that. I can choose arbitrarily. I can choose any coordinates that I like. I'll continue to stress that idea. But in terms of solving problems as a practical matter, I choose the typical math coordinates, and I like to put the origin right at the tail of my velocity vector at the initial position of the motion. As such, I can describe this velocity as having two components. A component that is directed along the x-axis, that I'm pleased to call Vx, it's a perfectly good name, and a component directed along the y-axis. And the whole idea here, is that I can treat the changes in these velocity components independently of each other. The changes that occur for the y velocity will have no effect whatever on the changes in the x velocity. So the very first task I have to do here is determine what these components are. Because typically what I'm told is that the velocity has some magnitude, the velocity of a cannonball perhaps, say some 20 meters per second, a spectacular launch of a cannonball, which also must have a direction associated with it, because vector quantities like velocity are a magnitude and a direction both. So my velocity vector here described by some angle theta, and so with a little bit of trigonometry, it's quite easy to see that since the x component of the velocity is adjacent to the angle, I can compute it simply as the magnitude of the velocity, which I'll simply call v, multiplied by the cosine of the angle. V cosine the angle, the horizontal component of velocity. It is a number that I have extracted from the description of the problem that I now know. The initial x component of velocity, if you like. I did not previously write a naught on there, so I should. The initial x velocity. And I didn't write them over here as well. I have sometimes a little crisis of notation. I should call that initial. I should call that initial. I should call that initial because I'm describing the start of the problem. So these are all initial quantities there. So a little addition to the notation. I probably ruined someone's notebook. I apologize. And of course, now that I've used the cosine component to find the horizontal, I could do a little bit, I could look at the diagram and make an argument about which side is opposite the angle or whatnot, but since I've already used the cosine, it's quite clear that the other component is found using the sine. At some point, I'm going to abandon, all those ideas of drawing triangles to talk about trigonometry and use trigonometry to its purpose. And this is typically what happens. I have an initial velocity at some angle, and I find its x and y components of velocity, and now I concern myself with how will those components of velocity change in time. Well, I can describe the motion over here. I've pre-drawn the diagram to ease my way a little bit. I have some projectile motion that has the very familiar parabolic looking sort of path to it. I haven't proven that it's parabolic, but we have a suspicion that when an object flies through the air under the influence of gravity, it kind of goes like a parabola. In just a few minutes, I'm going to prove that it does. Assuming that there's no viscous drag acting, that it moves in the shape of a parabola. But for the moment, I can appreciate this curve that I've drawn here and say, well, sure, maybe a projectile path looks like that. It seems to make sense. So here over on the left-hand side of the diagram is the initial part of the motion, the start of the motion, where there is an initial y velocity, so vy naught, directed vertically, and an initial x velocity, vx initial, directed here horizontally. Those are my initial components of velocity, and they'll evolve in time. I'll do the simplest first. How will the initial x velocity of the projectile change as time goes on? Well, the answer is interesting and trivial simultaneously. There is no x-axis acceleration. There is no influence that would change the horizontal velocity of a projectile. Do not think of it as math. Think of it as the nature of the thing. There is nothing that will change the velocity horizontally. Because the influence of gravity, I can observe from my everyday life, the influence of gravity is vertical along the y-axis. Being independent, the x velocity is unaffected. So it is a characteristic of projectile motion that I will take advantage of when solving problems, that the horizontal component of the velocity does not change during the motion. So the initial component of velocity, which I've already described, the recipe for computing, that initial component of velocity will persist through the entire motion. The x component of velocity does not change. That makes problem solving quite easy indeed, doesn't it? Anytime I ask for the horizontal component of the velocity, it is what it was to begin with. That's quite simple. It's one of the features of projectile motion that are worth knowing automatically, because you're apt to be asked questions about it. So that's one feature of the motion. Now, when I consider the vertical motion, it's a little bit more interesting because my acceleration is negative g in the vertical direction, the acceleration due to gravity. And so quite a sensible thing happens. If you look at the second instance here, compare the magnitude of these vertical velocity vector components that I've drawn. I drew it in such a way that it is now shorter. Now, that's not mathematical. I didn't calculate the length of that thing when I drew the diagram, but I made it shorter because I know that as the projectile rises, gravity will slow its ascent in the same manner that it does in free fall motion, because really, if I could ignore the horizontal motion of this diagram, I would simply have free fall motion, which I already understand how to describe. So as the projectile ascends, the vertical velocity is diminished by the action of gravity reducing the velocity in every second as it rises, negative 9.8 meters per second squared. But then ultimately, gravity will whittle away the velocity until I reach this point at the top of the motion where there is no velocity component vertically. The vertical velocity has diminished to zero at the highest point of the motion. That is another characteristic of projectile motion that I should always have in my head. Here's the thing. If I'm trying to write a clever exam problem that's going to catch a student in a misconception, I'll ask, what is the velocity at the top of the motion? And many students will answer that question, oh, it's zero. It's zero. And at the top of the motion, it's zero. It's not. While it is true that the vertical velocity component has diminished to zero, that is true, the horizontal velocity is not zero. This is commonly used as a trap. It is another feature of projectile motion, that at the top of the projectile motion, while it is true that the vertical component of the velocity is zero, the horizontal component continues to be the same as the initial component. And then I proceed on the descent here, and I see what happens. Now that I'm falling, in the same amount of time, you see I've placed these two positions, these intermediate positions, symmetrically. The velocity now increases downward, and so I have a small velocity component here directed downward, because as it falls, the acceleration due to gravity is increasing the velocity downward. Well, negative g, so I've subtracted velocity from zero, resulting in a negative velocity in my coordinate system directed downward. Speaking of symmetry, there's quite an interest here at the last position, where you see here on my diagram the height above zero, that is the y position of the projectile, is once again back to the same initial y position. And the velocity is directed downward and is considerable, because as it falls, it is gaining negative velocity the whole time. Well, here's an interesting symmetry. The final velocity at this end, I guess I'll call Vy, the final velocity at the final position is equal in magnitude to the initial velocity upward. It's simply in the opposite direction. And this is because the motion under the influence of gravity is symmetric. The change in velocity on the way to the maximum height is the same as the change in velocity on the way down, just as the time it takes to rise to the maximum height is the same as the time it takes to fall again to the same height. These are the characteristics of projectile motion. As for the first time, honestly, in this discussion, I'm thinking maybe I should make a list of those important characteristics. Let me see if I can repeat them as a list. In projectile motion, it is a characteristic of projectile motion that the horizontal component of the velocity remains unchanged. It is a characteristic of projectile motion that at the highest point of the motion, the vertical component of the velocity is equal to zero, but the horizontal component is not. It is a characteristic of projectile motion that it is symmetric. The time to rise is equal to the time to fall, and that the final velocity at the same height is equal in magnitude to the initial velocity, simply in the opposite direction. These are characteristics of projectile motion that someone skilled in this aspect of our physics will be well aware of. And so when that person sits down to write questions for ambitious students to answer, the questions will center around those ideas, those aspects. So it is important not to just appreciate the mathematics of projectile motion, but to appreciate its nature and to be able to describe it as I just have. Now for the mathematics. If I consider the kinematics of the horizontal motion of a projectile, it is quite simple. The kinematics of the horizontal motion of a projectile is quite simple because the horizontal acceleration is 0. There's very little math to be done here. There is no acceleration. And so I've written a summary here of equations that I might use to solve problems. And for the horizontal motion, you can tell because it's festooned with x's here, the horizontal position is equal to the initial horizontal position plus the x component of the velocity. I haven't written initial here. I haven't written final, 1, 2, or anything in between because the horizontal velocity of a projectile is the horizontal velocity of a projectile, and that's it. There is one number. That is all there is. Multiplied by the time. It is motion with constant velocity, the simplest kind of motion that I can describe, really, except for, standing still. But the simplest motion I can describe is motion with constant velocity. There's only one equation for solving for the horizontal motion of a projectile. The equations that I use to describe the vertical motion of a projectile are identically the same equations that I use for free fall motion. I've written them here in summary. I wrote them out in advance so I wouldn't have to spend time scribbling them down. We see y is equal to y naught plus v y naught t minus 1/2 gt squared, the minus sign because I'm writing it according to my problem solving strategy, which is always to choose upward to be the positive direction, and so on with the other kinematic equations. So when it comes to solving problems of projectile motion, there are only 4 equations that I need consider. So with a careful reading of the problem statement, organization of the information, choice of coordinate system, and the application of these equations, it should be a fairly simple thing, with a bit of skill, to arrive at correct and appropriate results. Along the way, I might encounter some more sophisticated problems that involve some algebraic manipulation. So what I'm going to do now is I'm going to describe the projectile motion with equations slightly more sophisticated than these 4 that I have suggested. I want to be clear. I can solve any problem of projectile motion using these 4 equations presented here. I don't need additional equations. But if I'm ambitious in my problem solving and would like a higher level of sophistication, I can sort of do some algebra in advance and create, in this case, a pair of equations that I can leverage to solve problems perhaps more rapidly or more transparently. Along the way, I'll make 2 important observations about the nature of projectile motion. Perhaps I would add those to my list of characteristics of projectile motion. Here I go. I'll begin by describing precisely the nature of projectile motion as being parabolic, because I suggested that it was so. And from your experience, you might agree that, yes, it goes up in a sort of a curving path. It looks very much like a parabola. I would like to prove, in fact, that it is a parabola. It'll take just a little bit of algebra and trigonometry. I'm going to begin, because if I want to prove that it's a parabola, what I need to do is I need to create an equation y is a function of x and prove that it's parabolic. You might say, no, Charlie, look, you've got y is equal to y naught plus v y naught t minus 1/2 gt squared. That's a t and a t squared. It's a parabola. It's a parabola in time. And that's great. It's a parabola in time. I'm interested in demonstrating the parabola in space. That is, I want an equation that is y as a function of x. But I will begin with my y equation. Let me begin this very essential derivation with y is equal to y naught, the initial y position, plus the initial y velocity, vy naught, multiplied by t, minus 1/2 of the acceleration, which is g, the acceleration due to gravity multiplied by time squared. Now, 2 quick adjustments to this equation. I'm going to assume, for my purposes here, that the initial position is equal to 0. That might not always be true in your problem solving, but in my problem solving it is, because almost always I choose the initial position to be equal to 0. So I'm going to strike out this y naught and call it 0. Also, I have the initial y velocity here. That is a component of the initial velocity vector. In fact, it is the sign component of the initial velocity vector. So I'm going to make that replacement in my equation. And so I'll write that the final y position is equal to v naught being the initial velocity, v naught times the sine of theta, multiplied by time, so I guess I'll need some parenthesis, minus 1 half gt squared. Now, if I'm to have any hope of converting this into an equation of y as a function of x, I'm going to need to do two things, and as it happens, they'll happen simultaneously. I need to eliminate t, because t is not my variable. I need to get some x into it, because x is the variable that I want. So I ask myself, do I have a relationship between x and time? Of course I do. Over here, drawing on a second equation, I'll sort of do this in parallel. The final position x is equal to the initial position plus the x component of the velocity multiplied by time. Again, a bit of simplification. I'm choosing the initial position to be equal to 0 because that's a choice. I get to make that choice. And Vx is the initial horizontal component of the velocity, and it's that component of velocity the whole time because the x velocity never changes. I know that the initial velocity vector has an x component that is the cosine component. So here I'll replace that x is equal to v naught times the cosine of theta multiplied by t. I've established a relationship between time and the x position. This is what I need in order to transform my y equation. So I'll solve this for t very clearly. T is equal to x divided by v naught cosine theta. That's quite obvious. And I want to make that replacement here into my y equation, but I'm also going to need t squared. I'm also going to need t squared because my equation has a t squared in it, and obviously I obtain that simply by squaring all of these parts. V naught squared cosine squared theta. That's rather obvious. I've simply squared that. So I'll make those substitutions into my y equation here, and it's going to become a little bit complicated? I don't know. It's going to be v naught times the sine of theta multiplied by x over v naught cosine theta minus 1 half g multiplied by the time squared. Well, I already worked that out for us. That's x squared over v naught squared cosine squared times theta. Now, I'm kind of done. I did what I wanted to do. I have y as a function of x, but let me gussy it up a little bit. Let me make it a little pretty. Because over here in the first term, I have a v naught in the numerator and a v naught in the denominator. I don't need that nonsense. They cancel, they vanish. I also have a sine theta divided by cosine theta. And whenever I'm doing physics on this level, from time to time, trigonometric identities will come in. It's not really my expectation now that you'll have trigonometric identities memorized, but I kind of like to think that everybody just loves the fact that sine squared theta plus cosine squared theta is equal to 1. That's a fun one, right? But there are more obscure trigonometric identities, which certainly are useful in physics, but having them memorized, you're okay. You'll memorize them through practice and experience when they come up. There's no reason to have, at this point, a great sense of urgency about it. But the sine of theta divided by the cosine of theta, by definition, is tangent of theta. That's not really an identity, more than it is like the relationship among sine, cosine, and tangent. So I choose to write my equation this way. Y is equal to, and I say choose because there's a little style. I'm going to write x times the tangent of theta because when I write equations, I don't like to have anything after the argument of the trig function because then I have to use extra parentheses and stuff to make sure I'm clear about the argument of the trig function. I put the x out in front. Now it's very clear. It is the tangent of theta only. Nobody was going to be confused about that. And I'm not wild about, a thing that you'll find that I like to do in derivations is I like to take the things that are constant and separate them from dependent. This doesn't always happen when people typeset equations, but it makes it easier to see what things depend on separate from what the constants are. So this last term, I'm going to write it this way. All of the things that are more or less constant, which I don't have it, assuming that I have that my initial velocity is a fact, and my initial launch angle is a fact, and I'm on Earth, the acceleration due to gravity, well, I guess I would use g, it doesn't matter. So what have I got? I've got g divided by 2 v naught squared cosine squared theta, and I put the x squared dependence off to the side like that. So I see that x squared dependence. Just as there's a parabolic nature to the equation for the vertical position in context of time, because there's a t and a t squared, this has an x and an x squared. And so I have proven here that in the absence of viscous drag moving solely under the influence of the gravitational force, indeed, projectile motion is parabolic in two-dimensional space. Oh, it's a proof. It also is, it turns out to be a useful equation. It's a ruddy big equation, isn't it? It's sort of unwieldy. If you have it memorized, it can often just one-shot a problem. Just boom, done. As opposed to going through the algebra. If you don't use this, you could still solve the problem, but you end up doing all of these machinations during the solution. And in particular, if speed is your interest, then using a problem like this would be, or using an equation like this would be a good idea. I like to refer to this equation as the trajectory equation. That's not official. That's just what I happen to call it. So I think we should be able to do that derivation without any trouble. A little bit of algebra, and now a bit of trigonometry as well. This is not the only interesting result that I can obtain, and indeed not the only practical result that I can obtain. I'm going to start again with another derivation that has the same feel to it. I'm going to be plugging one into the other, these things that I have defined and identified as characteristics of my projectile motion, and I'll arrive at an interesting result that I have to use with significant care because, referring back to this diagram that I have here, I want to solve the problem for the distance that a projectile travels over the horizontal here when it arrives at the final position at the same height from which it was launched. So imagine the battle takes place on a very flat plane and a cannonball is launched and it arrives at the same height from which it was launched. You have to be careful because when an equation is derived with specific assumptions, you cannot then go and use that equation all the time. A difficulty that I have in instructing students of physics is you devise a powerful equation that works in a specific circumstance, and then your students run off and try to apply it in every circumstance because the mathematics of it is easy, because it gets them a quick answer. Well, we're not interested at all in quick answers. We're interested in the correct answers, the appropriate description of the nature of things. So we'll have a care in using this. This distance traveled by a projectile horizontally from the same initial and final height, I'm content to call the range. And so I'm going to start with a description of that horizontal position of the projectile moving along with constant speed Vx over time. It moves with constant speed. And so now making adjustments to this equation, proceeding with my derivation. Once again, I'll suggest that this initial position is equal to 0. I'll suggest the initial position is equal to 0. That's assuming, once again, that I choose the origin of my coordinate system to be at the location of the launch of the projectile. And I'm aware of this initial component, just as I did in the previous derivation. The initial x component of the velocity is the cosine component. So this is v naught times the cosine of theta multiplied by the time. Once again, I do not want the time in my result. I choose that I don't want the time in my result. So what I'm going to do is use another equation that does have time in it. I'm going to go in a somewhat different direction here, though. And I'm going to say, I'm going to use Vy is equal to Vy naught minus G times T. And I'll use this equation to eliminate the time. But before I go and solve it for time and plug it in, a little adjustment to this as well. I have the initial y velocity that appears in the equation. And of course, I'll say that initial y velocity is the sine component, v naught times the sine of theta minus g times t. But recall, a feature of projectile motion, I think one of my themes for today across all the courses that I'm teaching is physics is not math. I'm describing the nature of things. A characteristic of my projectile motion is that when I launch a projectile from this height and it arrives at the same height again, its velocity is directed downward but has the same magnitude as the initial velocity, which means the final velocity for this equation, Vy, which appears here on the left, is actually negative v naught sine theta. It's the same velocity, simply in the negative direction. It's the same velocity, but in the negative direction. So when I do a little bit of rearrangement here, perhaps adding gt to this side and adding v naught sine theta back to the right-hand side, what I discover, if you don't mind me just taking the step, that I've discovered that the time is equal to 2 v naught sine theta divided by g. That is what the time is in fact equal to. And that's what I'll use for my substitution here on this side. I'll substitute in t. I meant to in a previous step right here that the x position, the final x position, assuming that the initial position is equal to 0, I like to call the range, and so I'll use a capital R to describe it. That's not official physics, that's just a style thing. I could leave it as x. But I like to believe that if I call it R, I'm going to remember that it's a very specific equation that should only be used under this very specific assumption that the initial and final heights are the same. At any rate, making the substitution, I have v naught times the cosine of theta multiplied by the time, which I just devised, is 2 v naught times the sine of theta divided by the acceleration due to gravity g. And I'm done! Except a little bit of gussying up the equation at the end to put it in a compact, the most compact and utilitarian form that I can. Notice that I have a v naught here and a v naught there. Surely that's a v naught squared. So I'm going to write my range equation just set temporarily this way as v naught squared 2 cosine theta sine theta, that whole works divided by g. Well, you might feel once again that I have a complicated looking equation. Not to worry. Here comes the trigonometric identity. I do not have an expectation that you will look at 2 times cosine theta times sine theta and know what that's equal to. But I'll give you a chance. What is 2 cosine theta sine theta? Anyone? It is sine 2 theta. Well done. Well done. So, the range of a projectile, and this, by the way, is my final result. The range of a projectile is taking 2 cosine theta sine theta and just calling that sine 2 theta, is the initial velocity squared divided by g multiplied by the sine of twice the launch angle. This equation I refer to as the range equation, and it often can be used to solve a problem in one go. Oh, well, Sally, then I'm going to use this equation all the time. No, because it's a catastrophe if you try to use it in an instance where the initial and final heights are not the same. That would be a disaster. It should only be used under those special circumstances, initial and final height the same. Hey, there's a bonus lurking in this equation. If I'm launching projectiles, I might have an interest in launching the projectile for the greatest distance, because the enemies, they tend to run away, in my experience. So if I want to launch the projectile for the greatest distance, what angle should I launch the projectile, assuming that my projectile has a certain, my launcher has a particular launch velocity, which they often do. I build a cannon, and no matter how I pack it maximally, the best velocity I can get is a particular velocity. I put a label on the side, this cannon, however many meters per second. What angle should I shoot at to maximize this distance? Well, if I have no control over the initial velocity, then v naught squared over g is going to be what v naught squared over g is going to be. What I want is the sine of theta in this equation have the largest possible value. Well, the biggest sine theta can ever be is 1, right? When is the sine of theta equal to 1? At 90 degrees. Oh, so you fire the projectile at 90 degrees? No, because the prescription of the equation is twice the angle. Twice the angle. Twice the launch angle. So I need twice the launch angle to be 90 degrees, which means I need the launch angle to be 45 degrees. That's a thing that I might have suspected, that the greatest range of a projectile is obtained when I launch at 45 degrees. If I launch above 45 degrees, it will land shorter. If I launch below 45 degrees, it will land shorter, because at 45 degrees is the greatest range of the projectile. So 2 times the angle would be equal to 90. So the angle would be equal to 45 degrees. Projectile motion. It's not rocket science. It's no rocket.